Design of heat exchanger in Aspen Hysys. We have following example for that. There is an example we are going to take, that is ammonia production using a Haber process, in which we take nitrogen from air and hydrogen, and we are going to mix it using a mixture, and then we will use heat exchanger, and where this mixed gas is cooled by water, that is a cooling water. Here is a simple flow sheet showing that, where the hydrogen is at 310 kilogram per hour flow rate and 230 degrees Celsius with 6640 kilopascal pressure. The same you can see for the nitrogen, that is 120 kilogram per hour, that is the flow rate, 200 degrees Celsius and 6600 kilopascal, that is the pressure. Both of the gases are going to mixture, then the gas mixture is then passed through heat exchanger. Here the cooling water inlet condition is 30 degrees Celsius and 10 atmosphere. The cooling water outlet condition is 90 degrees Celsius with 6680 kilopascal. Okay, and the gas outlet mixture is 57 degrees Celsius at 10 atmosphere. These are the conditions. We are going to make design heat exchanger, that is saline tube heat exchanger, and we are going to design it all the cells, and this all things will use the fluid package, that is Penn Robinson. Select new simulation, and what you have to do is that in the component list we have to add our three components, that is hydrogen, nitrogen and water. So search for hydrogen, enter, it will be on the list. Now nitrogen, and press enter, then water, press enter. All of the three components have been added, and now we can see green status is okay. Now in the fluid package we have selected Peng Robinson, so just find out there, okay, and just take enter. So now we can see the green, that means it is working. So now we are in the simulation area. This is a palette. Here you can see the material stream, drag it and double click, so you can see all the details for that. The first one is our nitrogen stream, nitrogen inlet, that is at 200 degrees Celsius and 6600 kilopascal, that is the pressure, and 120 kilogram per hour, that is our mass flow rate. Okay, now in the composition tab, that is nitrogen, so composition for hydrogen will be 0. Now enter the composition for nitrogen, that is 1, and for H2 that is 0. Normalize that and click on the OK, and you can see the green, that means all data are correct. Now add one more tab, and that is for hydrogen inlet stream. Okay, name it as a hydrogen inlet, then the temperature is at 230 degrees Celsius, pressure is a 6640 kilopascal, and flow rate is 310 kilogram per hour, that is mass flow rate, and composition for this is hydrogen mole fraction is 1, nitrogen and H2O mole fraction is 0. Normalize that and click OK. Now you see the green, that means all good. So now we have added two streams. Now we are going to add the mixture. Okay, select the mixture from this palette and insert. Now double click on that, name it as a mixture. Now inlet streams are our two streams, that is for nitrogen and hydrogen. Okay, and outlet stream is a gas mixture. Okay, we have to define that. Now you see the green tick, that means all are calculated. Now what we have to do next is we need three streams, that is for cold water inlet, that is second one is for cold water outlet, and the third one is for gas mixture outlet. Okay, so use the same procedure and The first one is a cold water inlet. So the inlet temperature is 30 degrees Celsius and pressure we keep as a 10 atmosphere. Okay, and the composition for this one will be 1 for H2O and the rest all are 0. We're going to normalize that and click OK. Now here is the composition unknown, some kind of error. Now we're going to add the water outlet stream. Name it as a water outlet. The outlet temperature we kept as a 57 degrees Celsius and the pressure we are not going to change, keep it as a 10 atmosphere. Okay, now we're going to add another stream, that is gas mixture outlet stream. Okay, gas mixture outlet stream, the temperature will be 90 degrees Celsius and the pressure will be 6680 kilopascal. Okay, and the composition we're not going to provide. Now we're going to add the heat exchanger. Simply drag this heat exchanger here and we're going to add all the streams. Okay, heat exchanger. Now we have to know the few things, which should be the tube side fluid or which should be the cell side fluid. Okay, for the tube side it can be corrosive fluid, or we can use a cooling water as a tube side fluid, or fluid that can cause fouling. The tubes should be on the fluid side because we cannot provide this fluids in the shell side. For the temperature of hot fluid, high temperature containing fluid, that should be on the tube side for the safety, and for the high pressure conditions, that should be on the fluid side. Low viscous fluids should be kept on tube side. For the highly viscous fluid, it should be on the cell side. Okay, these are few optimal things for better heat transfer between fluids that may help. In the more we can discuss on our book, that is Aspen, and so as we already discussed, the gas mixture will be on the tube side, the gas mixture outlet will be on the tube side outlet, and cooling water will be on the shell side. Cooling water outlet will be on water outlet. Now it shows that composition are unknown, so we're going to provide the composition by clicking on the worksheet, and we don't have composition for the cold water inlet, so we'll just provide that the composition. In the heat exchanger there is a composition on the workspace. So for the case of cooling water inlet, the composition of water will be 1 and another compositions are 0. Center that, click on the normalize, click OK. Now it shows green. Okay, all the fluid has been calculated. As we are going to see, this the color has been changed to blue. Using this auto position will help us to just look better. Now double click on heat exchanger. Let's see the various properties of heat exchanger. First of all, you can see that in the parameters there is a heat transfer coefficient, and you can see there is a 2 tube passes, 1 shell passes, and another thing in the rating you see that the overall heat transfer coefficient and heat transfer per shell area, tube volume per shell, and shell volume per shell. These all things are given. Tema type given. Shell, in the shell their shell diameter is given 739 mm. Number of tubes 160 has been calculated. Tube pitch 50 mm calculated. Tube layout angle triangular. We can change this and get another results and find the optimum. Now okay, these are the things, and there is a 4 option: square, rotated, and all. Okay, let's just close, and in the end I would like to show you the work table. Material stream containing all the data related to material stream. Another one is composition related. Composition are shown in the table for the whole process, and energy stream data for the whole process has been given here.